Okay, good morning, everyone. Today, discussion will be on, I would say, rather high level, general level, maybe more, one could call it a reliability philosophy. Discussing about the needs and challenges related to reliability. First, today I will start with the reliability challenges, where this basically where the needs are coming from, how the reliability science started, and then we also go will show a few definitions related to reliability, just to highlight that how you can, let's say, look reliability from several different perspectives. Then a few words on product life cycle, and especially some financial things related to reliability and product life cycle. And then finally, a few initial words on lifetime analysis. So which kind of tools we have in order to estimate or predict the lifetime, what kind of data we need, what models we have, and so on. If we have time, I assume not, then we could start the next topic on discussing why, where, and when the failures happen. But I think that's something that we need to leave to next Tuesday. Concerning the literature, I would say that maybe the best overall book for reliability engineering is this Patrick O'Connor's book, Practical Reliability Engineering. I think this is now, so yeah, 5th edition is there, maybe already 6th edition, but it basically contains lots of nice chapters, also from these topics which we are now starting with, and it has lots of mathematical tools. So in our course here, we are not spending too much time on these kind of, let's say, statistical mathematics, the ways of calculating reliability related things. I will, of course, show you a few case examples and show the basic methods how to do it. But the focus here, as I have tried to emphasize, is a little bit more on the physics of failure rather than statistical mathematical reliability. And then, of course, one nice piece of information is the military handbook. At least a few years back, if you Google smartly, you can find these military handbooks without any cost somewhere. So there's of course several different military handbooks, but this 338 is basically the main handbook on reliability. That's even the military handbook is sometimes a little bit outdated. The component libraries have not been updated for several years or even decades. Still, the basic approach for reliability is there, and let's say the more modern reliability tools, which I mean the reliability softwares, the approach is anyway based on the military handbook. So in that sense, of course, if I remember correctly, this is something like 1,000 pages long. So definitely not expecting that you would read it. But sometimes if it would be quite good thing to have, just to check things if needed. Okay, but let's jump to the actual topic. So as I tried to emphasize in the kickoff lecture, basically the reliability verification methodology is relatively simple. So we always have these basic parts of reliability analysis. So first of all, of course, we have the actual product. So whatever it is, so it has certain geometry and it has certain materials, and the materials have certain properties. So that kind of provides the basis for reliability analysis. And then we have here in the right-hand side, we have the stresses. And here in this picture, it is only showing the environmental stresses, but of course, we also have the so-called operational or functional stresses. So those which are coming from the actual product itself, like power losses causing increased temperature. And then based on basically the materials and structure and the stresses, then we can formulate some kind of a model or prediction or analysis. So in this case, it's the stress analysis. So when we have temperature and temperature is changing, how the temperature is distributed, and then what kind of thermomechanical stresses, for example, the changes in temperature cause. So that provides kind of the basic information for then having some kind of model for analyzing, for example, the lifetime. So this stress analysis provides the input for some kind of a lifetime prediction model, which in this case is really simple. It's based on so-called Coffey-Manson equation. So here NF is, as always in the reliability models, it's the number of cycles to failure. So F means failure and N is number of cycles. So how many times the temperature goes up and down before the system fails. And then we have two constant A and B, which is completely dependent on, for example, on the geometry and material. So there's no basically no physical link to the real physical world. The only physical parameter here is the epsilon P, and this means the plastic strain. So it means that how much in a certain position the material deforms plastically in one cycle. So the idea of this model is that every cycle the material deforms a little bit without recovery. So plastic means that it does not recover. So basically the failure accumulates. So every cycle more and more deformation is accumulating. So we have a cumulative failure, and then after certain amount of failure, then we kind of reach the limit, and then it fails. So basically, if you would just have a pen, there is the camera there, you start bending this one, and then if I would bend hard enough, every cycle, this upper surface would stretch and leave some permanent deformation, and then we would basically have a critical value that, okay, when this is the upper surface has stretched so much that a crack will form, and then maybe after next cycle it would be completely broken. Okay, of course, my plastic pen is not a very good example because typically these kind of plastics are very not that sensitive against fatigue. Maybe a better example would have been this kind of a there is again, okay, it doesn't focus on this one, but this is a metallic pen. So fatigue would be kind of the main mechanism. And then I see that there's a question in the chat, what is considered as a cycle? So cycle, there are different, let's say, definitions of cycle, but in these kind of models, one cycle means that when temperature goes up and down. But of course, in real life, it is not simple as that. Maybe, sorry, I'll take the pen. If I manage to do it. Just a second. Now, pen, try to draw it somewhere. So basically, a simple case would be that we have like this is time, and this is temperature. And if we are, for example, in testing, so thermal cycling, then it should be quite simple. So we put do it like this. This could be, for example, 125 degrees centigrade, and this could be -40. So this is maybe the most typical common thermal cycling test, which is in IEC standards, JEDEC standards, and so on. And then one cycle would be from here to here. And then we are doing it, for example, in standards, it's 1,000 cycles, 2,000 cycles, or whatever, and then that should reflect to certain lifetime or certain lifetime in real use operation conditions. But if we think what is really happening in the real operation, then let me see if I can have another color. So then it most probably it is something like this. Okay, sorry about that. There's something. Mouse is jumping, but maybe you get the idea. So we have, let's say, these kind of maxi cycles, and then we have mini cycles, and these mini cycles can be, for example, coming from the power losses. So basically, when you in your mobile phone, when you download a video or whatever, then of course your phone is using a little bit more power, and then it heats up a little bit more, and this kind of thing. Or when you make a phone call, so then the temperature is higher. And then if in the testing, this one cycle here could be, for example, let's put it 30 minutes. So 12 minutes up, 12 minutes down, and then ramp up and ramp down. So in real operation, this could be, for example, this could be, for example, 24 hours. So this is basically could be your office hours or day when you are using your device. This could be the night time where you are charging your device. It's basically not operated. So for example, then maybe my example was not that good, but here, for example, these mini cycles would be much less. Only if somebody sends you a WhatsApp message or whatever during the night time, then there might be a small change in the power, but in the daytime it could be much larger. So basically, then the point here in the lifetime prediction or whatever would be that how do we correlate these one? So we have a test. We do some testing, which is, of course, needs to be accelerated testing. So accelerated in that sense that, for example, we use higher temperatures and lower temperatures, and then we should have some kind of a model which takes into consideration. In the end of this lecture, I will show you a few very simple examples, and then, of course, in the second part of the course, we go into much more detail on these things. Okay, maybe I will switch back to the laser pointer because it starts to be quite confusing. Okay, so my point here was just that you need some input data, then you do some analysis, stress analysis, then you have some models. Based on the models, you make predictions. You think make the decision, is my product reliable enough or not? If not, then what will be the actions? How do I improve it? Change the design, change the materials, do something else, and then you end up having reliable, optimal design. So this sounds very simple, but in practice, it's not, unfortunately. So first of all, I would like to say a few words on why electronics reliability is difficult. I added the engineering word there in the title. It could be verification, whatever, but the idea is that what kind of challenges we have in order to really make sure that the products are reliable. So I put here 4 things. These 4 things: complex systems, discontinuity in design, heterogeneity of materials, and nanometer level fault tolerances. I think these are a little bit looking in the towards future. What kind of challenges we face when we are designing new products, novel products, and so on. If we think about just what are the challenges having high reliability in, let's say, current products, then of course we are missing here. This is not a complete slide in that sense. So, for example, one very good example on what is really a challenge in verifying the reliability of let's say products which are already on market is the let's say monitoring of the field failures. So even most of the companies, even the biggest ones, they claim that, okay, we are monitoring the field failures. Yes, everybody is monitoring the field failures, but in what level? So typically, if you want to really improve the reliability, you really need to understand why something failed. Not how it failed or where it failed, but why it failed. And that means quite detailed information. Maybe as an example on car. So if you go to the car, this yearly inspection, if your car fails, you get a report that, okay, the brakes were not good enough. Your handbrake was not strong enough. Then, of course, you can record that the problem was handbrake not was strong enough. But that's not, let's say, accurate information in detail how you would improve it, because there might be several reasons why the brakes are not strong enough. The handbrake is not strong enough. It might be stuck. It might be the plates have been worn out. There might be some problem in the wire, several different things. So in order to, let's say, fix the problem, you need to go under the car and see, okay, what was the problem now? Or in more generic level, then how you would improve the situation in those products which you are now manufacturing, or those products which you are now developing. So quite often, if something fails in the field, the company sends there some repair engineer or whatever. He or she measures, okay, this part is broken, puts a spare part there, and writes a report that, okay, the power source was had to be replaced. And then the data is that, okay, the problem was in the power source. But that's all. So if we want to improve the reliability, then we need more. So we need exact details on what was the problem in that power source, why it had failed. And that typically means that the broken part should have been sent back to some kind of a corporate research center or some place where failure analysis could be done. And then you would kind of do the structural failure analysis. But in addition to that, you should also collect the history of that specific part or device. So you would need to know that, okay, how long it was operational, which kind of conditions, what were the mission profiles, anything specific happened which could cause the problem, power surges or something like that. And then one could kind of really brainstorm that, okay, was the problem wear out, so that just that the product aged, or was it so that there was some kind of a robustness problem, so it kind of, for example, saw an overstress or combination of that. Okay, my example on power sources, I think that at least some of you also have this experience with your desktop computers. So at least we have had in the university several cases where old computers cannot withstand the let's say sudden electrical blackouts. So if because of some infrastructure problem or thunderstorm or something like that, the power goes off, jumps back, there's typically a small peak in the voltage, the old power sources of our old computers, they broke. Why the new ones don't? Are they more robust? Or is it something that basically we already have consumed so much of the lifetime that this extra stress does kills the product? So these are let's say examples that are the typical challenges for let's say today's products. But now with these next slides, I would like to highlight a little bit more on what are the things related to reliability challenges if you are developing something new, or if we are there in the, let's say, high-end products. And I have just few simple case examples here. So let's start with the complex products. So of course, this is not the newest miniaturized handheld product, but still I think quite good example. So for a complex product, my example here is now the main board of Samsung Galaxy Watch, and there the main component, the brains of the components. So sorry. Here we have the why I'm having it, maybe to mention that I think 3 years back we made a reverse engineering on this product in Glenn's course, Materials and Microsystem Integration, and now 2 previous years we have used the data in Mervi's course for making the life cycle analysis, or was it the iPod? Okay, anyway, but the point is that this is the data is coming from our own reverse engineering, and you can see that even this kind of not that expensive product is really a very complex one. And here is the trans illumination X-ray just from the whole motherboard, and here is the actual Exynos IC containing both the logic part and the memory part. And if we look the cross section of that component, so we see that this is so-called fan-out panel level package. Glenn will be discussing much more on these things in MMI course, but the point here is that first of all, it's a panel level production, which means that basically these components are not manufactured kind of one by one or packaged one by one. Of course, the actual ICs are manufactured in wafers, then diced, but then when you make the package, it's not that you have one chip and you package that one, like which is the traditional way. But now this is panel level packaging, so the panel size could be, for example, 1 meter times 1 meter, and then you have this package, which is something like maybe 2.5 centimeters times 2.5 centimeters. So you can calculate that how many centimeters we have. 4, then it's 40 times 40, so it's 160 if I calculate it correctly. So from one panel, one gets 160 components. So this is of course one way to minimize the manufacturing cost. Maybe my math was wrong, but at least something like that. So that is one thing. Of course, to verify that these kind of very complex structures can be manufactured with high yield with this kind of methods. And the other thing is, of course, that when we think about the structure here inside, it is relatively complex. We have the interconnections from the component to the motherboard, and we have different solder joints. We have wire bonds here. We have the actual chips, and so on and so on. I don't want to go on the details now here because we are coming back to these issues several times in this course and in Glenn's course. So then maybe we could use the previous picture also from this viewpoint that the heterogeneity of materials. So when, especially the miniaturization, we want to have more functionalities in a smaller space. We want to have less power consumption, and typically power consumption also is kind of improved when you miniaturize something. So it means that we need to use relatively complex material stacks to achieve our targets. So if we think about the electronics 20 years back, we think about the interconnection. So how you connect component, another component, and the printed wiring board. There was only, I would say, one or two options. You always had thin lead solder, because it was very good. And then you had your component metallizations, which were either copper or they were nickel, or copper and coated with nickel. So basically your, let's say, material options were thin lead plus copper or thin lead plus nickel. Maybe sometimes nickel was coated with gold, but anyway. So only 2 or 3 material combinations which you need to understand under different loading conditions. But now if we, for example, think about this kind of a structure, so this is so-called all silicon package, which was kind of, this is not a real product, definitely. This is something that the vision is that something like this will be there in the miniaturized products in the near future. And the concept was presented in this book. I think it's excellent book in that sense that it contains lots of nice things related to our field. Mervi is one of the editors. I was part of 2 chapters, one on bonding techniques, one on MEMS reliability. So if you have the time and need, I think this is this available as an ebook. I'm not sure, but at least the content should be visible, and if needed, that should be able to, you should be able to borrow that from the library. But I'm sorry, I'm not exactly sure. So here, this kind of all silicon package concept was kind of proposed, that we would have in a stack of components, so that we would have. There's a question which chapter. So basically, if you want to just look the future trends, then it's the first chapter that presents this concept of silicon packets. It's quite wide book, and most of the other chapters are related to certain technology. So of course you shouldn't look through all, but if you are then later on interested, for example, on silicon and insulator structures or different processes like sputtering or gettering or whatever, there are good starting material for these kind of things. So for example, this in general microfabrication techniques. So this is especially for our SSI students. So if you don't have the background on microfabrication techniques, and our AE students, at least those who want, can have that course in springtime, but you will also get it in Norway. But in order to have kind of the first ideas on for example, how these microfabrication processes like silicon etching or whatever is functioning, this is very good source book for that. But of course, you have limited amount of time, so I would use it as the name says, handbook. So handbook is a book that if you need to know something, then you pick up the handbook and quickly check it and put it back. Not that you start reading from the first page. But for this kind of a future trends, maybe it would be good to read just is it the introduction chapter or chapter 1, which proposes this one. But the point here is that, let's say one package, we have practically all, in quotes, all functionalities. So we have, of course, here in the bottom, we have the actual logic, so processing, memory, whatever. Then we have the necessary capacitors, necessary passive components like capacitors, resistors, inductors, whatever needed. Then one might have some energy harvesters, supercapacitors, or whatever to really be able to live without external power source. Of course, what could be added here is the radio part. So we need some kind of a data transfer. Then we might have something which measures the environment. So here one could have, for example, inertial sensors like gyroscope or accelerometer. This could be some kind of an optical MEMS like microbolometer measuring the ambient temperature. So thermal camera in practice for these kind of things. So if you would like to have all these integrated into one package, then you need quite, let's say, novel material selection. So just as an example, if we think about this tiny part here, which is the hermetic encapsulation of its MEMS component. So because this microbolometer as well as this gyroscope, they need to operate in a very high vacuum. So it means that in order to really have an accurate enough thermal image, this thermal image sensor needs to be in a high vacuum. And how you achieve it is that after manufacturing the actual component, you make the hermetic encapsulation so that here we have the glass cap, and then you bond it. So this is so-called sealing frame here. And now the structure here, how the sealing frame makes the hermetic contact with the substrate is shown here. So what kind of different materials? So we can have the silicon or silicon dioxide, then we have a diffusion barrier, adhesion layer, tungsten, nickel, gold, tin. So these are the actual bonding materials, gold, tin, bond. Then on the other side, we have some metallization, which is compatible with this bonding material. Could be, for example, platinum, again, adhesion layer, titanium, molybdenum as a diffusion barrier, again, adhesion layer, titanium, and then silicon again. So, and this total height could be something like what I would say 8 micrometers, 6 micrometers, something like that. So typically gold, for example, 4, tin, maybe 2, nickel, few hundred nanometers, and the rest of them are maybe less than 100 nanometer thick. So it means that the whole height would be, let's say, clearly below 10 micrometers. So you can really understand that the materials compatibility needs to be understood really well, and we need to understand how this kind of a material stack behaves under different kind of stress conditions. Of course, first of all, this is not stable. So after bonding, already we have some reactions. So we don't see there any more tin at all, because tin has been already consumed completely with the reactions between gold and platinum. And all these materials have, for example, different coefficients of thermal expansion. So when you increase the temperature, they expand with a different extent and rate. And so this is kind of a local CTE, coefficient of thermal expansion mismatch. But then we have also global one, because here we have glass, here we have silicon. Silicon has the CTE of 2.8, and glass has something like, depending on the glass, typically something like maybe 6. So it means that when we increase the temperature, this glass expands something like 2 times more than the silicon. What it means that is stresses are formed somewhere. The glass wants to kind of bulge up, and sooner or later something will fail. And this is something that we need to verify when we are talking about reliability engineering. So we need to understand these things. We need to understand the large variety of materials, how they are compatible with each other, how they are reacting with each other, and how they are behaving under different types of stresses. Discontinuity in design. So this is maybe more related to the fact that we are going into smaller and smaller dimensions. And quite often our models are quite simplified. So for example, we have layers of different materials, and then we change the temperature and see how these expand and see the stresses. But actually, in real products, the structures are much more complex, three-dimensional, having multiple different materials. And this is a case example already a few years back from a commercial power component. So basically, this is a maybe power MOSFET, if I remember correctly, or was it IGBT, and it's packaged in this kind of a very standard surface mount package where you have the leads. So this could be, for example, QFP component, and because it's a power component, so lots of power losses, one needs to have also here a large copper heat slug underneath to let's say get rid of the extra power losses which is formed here. And what this company, this is an let's say published data. So the problem was in Infineon, and they published in fact 3 papers on this problem and the solutions. But what they observed was that when you are doing power cycling on this kind of a structure, so power cycling of course means that you are using it in real operation. Power goes up and down, temperature goes up and down, and what happened was that the passivation layer, which is on the top, started cracking like this. So maybe you can see here the surface is full of cracks, and if we take a cross section from this corner, we see that here is the aluminum conductor, and here is the silicon nitride passivation, and you can see that in fact the silicon nitride passivation has cracked completely through. So basically here now we have a direct path for humidity and impurities to attack the aluminum metallization. So even at this stage, this product or component could be operational, but sooner or later it would fail because of the, let's say, cumulative effect of stresses. And in fact, the problem here was that because of this kind of a cyclic loading, temperature going up, down, this aluminum here starts to deform. So every cycle, basically the aluminum changes its shape, and in fact, it kind of pushes the silicon nitride outwards. And of course, silicon nitride is extremely hard but brittle ceramic material. So after certain, let's say, amount of stress, kind of maybe again 10. So the kind of the force is will be something like this. So because of the aluminum deformation, this part here is kind of pushed outwards, and then that silicon nitride cracks. So this is one way of let's say, thinking that how the actual design, the structure, the geometry is making reliability engineers' life quite nasty. Here is an example of, let's say, faults, different kind of defects. So again, this is this is somewhat related to miniaturization. So when all the dimensions let's say, go smaller and smaller, then of course smaller amount of defects are also causing reliability problems. Maybe the best example could be if we take these novel transistors. So for example, what is now it's 7 nanometer technology or 5 nanometer technology or whatever is the state of the art. This is definitely not my field of expertise, but the let's say effects and the quality of gate oxide in our modern transistors, that's a critical thing. So kind of the manufacturing methods and the materials used there, they have developed drastically. So if I understand correctly, for example, hafnium oxide made with ALD technology is now let's say the use there in the gate oxide in order to really make sure that the gate oxide functions. So there we are talking about defects in an atom level. So not even in the nanometer level, but in atom level. But here my example is on interconnections. This is coming from our own project, which ended I think 2 years ago. It was together with VTT, Murata, and Augmetic. So our intention was to demonstrate a gyroscope bonded with polysilicon TSVs. So basically the cap wafer here is from Augmetic. The device wafer here, or the design is from Murata, and VTT manufactured this one. So here you can see the actual gyroscope structure. And also here the gyroscopes needs the hermeticity, the vacuum to operate. So how this is made was this kind of a hermetic sealing. But now in comparison to my previous example where the hermetic sealing was only for hermeticity, here the target was to have it also as an electrical contact. So basically here you see the TSV, so true silicon bias. So the idea is that the electrical contact to the resonator of the gyroscope is made from here like this. So what we observed was that at this bond here, there was lots of voids, like you see here. In fact, the major problem was not these voids, it was these cracks here. You see the pointed with the red arrows. So in fact, that caused the initial problem. But also you can see that there's quite a lot of voids here in this structure, and the source of the voids is from electrochemical copper plating. How you control that one, how you control the impurities, and then how this, let's say, microstructure is formed during the bonding. So the point here is that we will see that these kind of defects, you could as easily see those in your 70s radio from 70s, which used the copper tin lead solder and copper component leads. There could be the same problems, but because they are minor, there's lots of soft tin lead there. So at least they did not cause any mechanical problems, and also the electrical contact area is so large that they don't, in practice, increase the resistance at all. But here we can have several different effects, because now they can already, let's say, decrease or increase the resistance, because they take quite a lot of cross-sectional area. So basically these are air inside. So these parts where you have the black dots here, they are not conducting electricity. So for example, here quite large fraction of the cross-sectional area is covered with the voids. So it means that your resistance is higher, which can then cause power losses again and again. Or it also means that your mechanical strength is less if this would be the weakest link in the mechanical structure. Now it was the other parts which failed, but anyway. So the point is that now when you look a little bit closer, you see that these defects, this is the 200 nanometer bar. So maybe one could say that the average size 10 nanometers, 20 nanometers or something like that. So it means that your manufacturing process must be much tighter control than ever before, because you cannot allow defects in that extent that was acceptable in earlier generation products. Okay, then a few more case examples on where kind of this industry is heading, or which can be the most challenging applications. So this is something which is not in the market yet. It is something that several research groups in the world are developing. It's a LiDAR component, so light detection and ranging. So the main application, of course, is for autonomous driving. Yes, we have LiDARs already in today's cars, but the problem is that they are really expensive. We are talking about component price, at least hundreds of euros per component. So it means that you cannot have it in let's say cheap cars. It's okay to put 4 LiDAR components in a Mercedes-Benz or BMW, where if you need to add 1,000 or 2,000 euros for a LiDAR system, may not be that big of an issue. But if we want to have autonomous driving, and we could have this kind of a radar systems also in every car, we need to really decrease the price of the actual component. And MEMS, again, micro electromechanical system, or in this case, I think it's MOEMS, so micro electrical optical mechanical system, is one option. So that because in LiDAR you need moving mirror. So in current LiDARs, typically the mirror is moved with, let's say, traditional ways, mechanics and electric motor. So there's something which you have a small electric motor which scans the mirror. But of course, in order to allow millions or even billions of cycles, because you need to scan during the whole lifetime, then MEMS is a good option, because silicon itself is an, I would say, ideal spring material. It does not fatigue at all. So that's the reason, for example, it is used in gyroscopes and so on. But you also need to have, first challenge is to have controlled movement with some means. So how you bend or not bend, move this mirror like that. So you need to have some kind of a material like piezo material which causes the movement, or you can have, for example, capacitive actuation. The other maybe more important problem is that of course these kind of solutions already exist in gyroscopes, for example, or accelerometers, or some other products. But here we need large movement. So the angle is large. So what it means is that one needs to have very large cavity where this movement is done. And that in practice causes lots of challenges in bonding, in hermeticity, in stresses, and so on. So this is something that people are working. Also we, at least partly. Then the other thing is that you need the electrical interconnections. So just by being able to move the mirror, then you need to have, of course, the laser source, and then that is the outgoing beam, and then you have the reflecting incoming beam, and then you need to have some kind of a photo detector. But you need to have the electrical connections. So you need to have the electrical connections for the actual mirror, control it, and then of course the other electronics. So again, you need to have, let's say, very advanced structures like silicon insulator structures, how you manufacture this one, the mirror. You need to have the electrical contacts, different types of microbonds, and you need to have also vertical interconnections. So horizontal interconnections, they are something which already exist. You will see during this semester some structures where, for example, in gyroscopes or accelerometers, there are horizontal interconnections. So basically, that the actual MEMS part is connected electrically horizontally, and then somewhere here is wire bond or whatever. But in order to really miniaturize and have more freedom in the design, then you also need vertical interconnections. And then you need these wires. And typically, as our materials are silicon-based, then we are calling them true silicon wires. But basically, the idea is just that with one way or the other, you can make vertical interconnections. If you Google again, you will find these kind of structures in stacked memory components already. So basically, also that technology exists. But when we are going to MEMS structures with more different types of materials, then there's still lots of challenges to be solved. Okay, and then one more, let's say, just a quick look on how the modern highly integrated structures could look like. And even this is from Galaxy S8, again, a picture which we have taken with the students maybe 5 years back or something like that. So this is just a cross-section from the motherboard. At that location where we have the actual processor component, which is here, and then on top of that processor component, there's the memory. So stacked memory. So this is the actual motherboard containing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 layers. So the motherboard is 12-layer board. Then we have the substrate for the processor. The processor is here connected with these micro bumps, and then 2 memory components which are stacked on top of each other and connected via wire bonds is then bonded on top of this processor component. And then we have some passives underneath on the other side of the motherboard. So this just kind of shows that, okay, the structures are really complex. How do you verify that this is a reliable structure, for example, when you drop your phone? When you drop your phone, it can, the maximum deceleration, the G values with a phone can with face, if you drop it from 1 meter height, could be as high as 8,000 Gs. 8,000 Gs. So that is really like a rocket launch local. So it means that we need to make sure that all these parts are reliable against that kind of shock loadings. Okay. So now let's. I have spent a lot of time in motivating or saying what is difficult. So how do we then proceed? How do we go forward with the design for reliability? So let's start with the first formal definition. So I think I have mentioned this already several times, so I'm not going to go through this in detail. So basically, the idea is that you have a certain structure, you have certain materials, you have certain parts, you use certain manufacturing process to put them together, and then you think about your use environment, and you try to make sure that even in the worst case scenario, this product is reliable enough. So in order to do this, we need to do at least these things. We need to understand the actual operating environment. We need to have a clear definition what is our requirements, expectation on the lifetime. we need to have models, reliability models, lifetime models, which are usable for these kind of conditions and these structures. Then we can make some estimations on the lifetime or useful life. And then if we see that, okay, this design should be feasible, then we do a verification, we do accelerated testing, we do different type of analysis, then we might need to do redesign and so on. We might do stress derating, which means that with way or the other, we, let's say, control the stresses, like putting a cooler or improve the thermal design, or then if we have design or components which are specified in the higher temperatures, then we can basically add extra lifetime, possibly by using them in the lower maximum temperatures or something like that. And then we also always need to think about robustness. So if the words are not familiar to you, so reliability, lifetime, we typically think about wear out, so something which is kind of accumulating during the usage. And then after a certain amount of cycles or years or hours or whatever, then the product comes old and it fails. But then when we are talking about robustness, it is basically how reliable the product is against overstresses. So just one peak, one single bullet, one extra stress which could kill them. So this is again a thing which we are coming back several times during the course. So I have shown this similar type of triangle several times, but this now has a little bit more focus on power electronics. And why I wanted to put here is that a new thing in this kind of a reliability, a new thing, it's not new in that sense that, for example, in military, for example, our Hornets, they already have had this kind of a health monitoring, condition monitoring already for 20 years or something like that. But it is kind of expanding to other fields where also costs matters. So here these two blocks are the same as what we have already seen several times. So different kind of design related things, the analytical physics of failure analysis, but here the third part, which in quite many times this is related to testing. Now here they want to emphasize the condition monitoring. So either you are following the normal operational parameters, and based on those, you might start seeing anomalies, which could indicate that something starts failing. Or then you do it a little bit more cleverly, and you integrate some sensors, for example. You could integrate a humidity sensor in your printed wiring board. You could have an additional temperature sensor in your power IC, which actually measures the junction temperature in your power component, not that you measure the temperature of the heatsink, which is, of course, then if you want to know the actual junction temperature of the power component, then you need to model it. You have certain thermal resistance path, which you need to model in order to really so you can either try to figure out what is the actual peak temperature there by monitoring some electrical parameters, for example, the collector emitter voltage, which you cannot do when the system is let's say, ongoing. If I have understood correctly, you need to stop it and then measure it and have a reference value for that one. Or then you measure the heatsink temperature, and then you have a model which tells you that, okay, if the heatsink in this external temperature, heatsink temperature is this one, then the junction temperature should be that. Or then even better, which is already used in automotive, is that you in the chip you have a kind of extra temperature sensor which you can monitor in situ all the time and follow the temperature of the IC. So that would, if that starts to increase, then you know that, okay, something is happening. For example, your die attach or your thermal adhesive starts aging. So sooner or later, the smoke will come out. And then you, for example, can, based on that, you can say that, okay, now we need to change that part. So you don't get a fire. Instead, you need to change the part. Okay, so this was just one minor thing. That this is something which is coming more and more and spreading all over the industry, not only on this, let's say, the highest reliability requirement or things where the cost does not matter, like military and avionics space, for example. Okay, sorry. Yeah, so Sakari is also asking about thermal throttling in computer components, typical case of controlling monitoring. Yes, that is kind of one thing which you can consider, that it is similar type of thing. Of course, there, if I have understood how it is done, it's kind of, again, you don't actually measure the temperature in the actual processor IC, but it is, let's say, the measurement is somewhere else, and based on that, then you think, okay, how, because the processor ICs, they are typically rated as the maximum junction temperature of 125 in commercial, if I remember correctly, might be some cases higher. But basically, then this is what you use for if you're, for example, overclocking your computers, how you can control that, okay, how much is possible, and where basically then you start drastically decreasing the lifetime, or when you basically go to the overstress situation that immediately something is failing. But definitely this is, again, not my core competence field, this desktop computers and how you manipulate those. Okay, then just I noticed that last year or previous years I kind of have missed. I'm using several words which there might be some confusing what they exactly mean. So therefore I put this slide here. It's stolen from Calse, University of Maryland, which is kind of the maybe considered as the reliability pioneers there. So Michael Pecht there has done excellent work during the years, and in fact the health monitoring is something that they have worked a lot during the maybe last 5 or 10 years. So if you are interested in health monitoring and you Google, most probably you will end up finding a lot of data from Calse and Michael Pecht from University of Maryland. So first of all, what I would like to highlight is the difference between failure mode and failure mechanism. Unfortunately, quite often in the literature, these are mixed up. I try to be consistent now in this course that when we are talking about failure mode, that is the effect how the failure is observed. So for example, most of you are electrical engineers, so for you maybe an open circuit is quite obvious, or short circuit is an obvious failure mode. So it means that you measure with the multimeter and see, okay, there's a short circuit. That's a failure mode. But the failure mechanism is the reason why this short circuit has formed. So this short circuit could be, for example, a corrosion product shorting through 2 lines. So something growing here and making the contact. It could be a thin whisker growing. It could be some external particle short circuiting or whatever. So the mechanism is some kind of a physical or chemical or thermal or thermodynamic or whatever reason why this failure mode occurs. So please pay attention to this one. Then the other thing is that we are talking about stresses or loads. And now quite often in our normal life, we think stresses that they are mechanical stresses. Someone is bending something or stretching or whatever. But when we are talking about electronics reliability, then our stresses are really whatever loads and how high. So basically we have a load, for example, temperature is a load, and then high temperature or low temperature is a stress. So the extent or the intensity of the load is the stress. This might sound a little bit strange now, but you will figure it out during the course. So we need to consider the stress in a wide perspective. Okay, so let's go forward. We still have a little bit more than half an hour time. Sorry, I'll take a sip because my throat is killing me. Okay, so few words on the need for reliability. Okay, this is now coming back to the reliability physics and where everything started. And I don't want to spend too much time also here, but just a few numbers which kind of highlight where and when this reliability, again, I want to put it on quotes, science. Reliability engineering is not science in that sense, but where everything started. It was that after Second World War, the US Army noted that, okay, our products were not available. Availability means that the products are there and they are working when you need them. So in fact, less than 40% of all Army equipment were not available. The electronic equipment in US Navy, the availability was something like 70%, meaning that 30% of the equipment were not available. Maybe most staggering information is the next one, that more than 60% of equipment which were shipped from US to Far East arrived damaged. So basically they were functional when they put into the ships or planes, and then when they were in the Far East, somebody started to use the radio or whatever, then it did not work. So more than 60% kind of failed during the transportation, storage, and so on. The MTTF, mean time to failure for bomber electronics, was less than 20 hours. So thinking about the planes at that time and typical flights durations, then almost every flight, the electronics failed at least once. So for example, radar. If that fails, then where you drop your bombs? That is really was a big issue. You can't just randomly drop the bombs wherever, because then you might be dropping them over your own troops, which happened a lot, unfortunately. And then the final thing was that they also realized that the repair and maintenance cost was more than 10 times of the original purchase price, meaning that if the products would be more reliable and robust in the first stage, then maybe they would be more available and the total cost would be much less. I have some additional slides coming up in a minute on this topic. But what I would like to highlight related to this one is that this also comes back to the reliability monitoring and inspection testing during the production. So here is just an arbitrary data from relative cost of a found defect. So this could be, for example, it could be, for example, desktop computer. If you have a problem in the motherboard of a desktop computer, then if you can detect it immediately after the motherboard has been manufactured. Or this could as well, let's take your iPhone, your newest iPhone. So the motherboard size like this, and maybe the actual cost of that board is a few euros when Apple is purchasing from someone. So if you can find the problem, for example, a bad connection between the layers in somewhere inside the board, which is not that simple to detect. We will see it in the third part of the course. But anyway, so if you can find it, you just scrap the board because it's basically unrepairable and take a new one. Your loss is €1, $1, whatever. If you assemble all the components there, so do the surface mount manufacturing, and then you put it in the test bench and you see that, okay, there's a problem and the printed circuit board is not failing, then the cost is already at least 10 times because you already have there more than 500, maybe 700 components. And that's, of course, most of them are passive components where the cost is something like 0 something cents, but you also have there dozens of ICs. Maybe you can take some 2 or 3 the most expensive components off and reuse them, or you just scrap the whole board. If you have the whole system assembled, meaning that somebody has then attached the battery and the display and put the covers and everything, and then you figure out that, okay, first time you test the phone, then it fails. Then it's already, because you need to add the labor cost there also. So then maybe we are talking about another 10 times increase in the price. You need to throw it away. Because as I said, this problem is unrepairable. It's in the motherboard. Then, if you still do not detect the problem, but the product goes to the customer, so it is shipped from somewhere from the world to the other part of the world, and then your customer purchases it, start operating it, and after 1 week, it fails. It might be that it can survive a few times on and off, but every cycle, this defect is increasing, and then it breaks in 1 week. Then the cost might be even higher. So because now you also need to include the indirect cost of reputation and so on. So it means that we also need to be able to find the problems early enough in order to be cost efficient. So all this kind of highlighted that, okay, we need to have reliability tools, we need to have models, mathematical models, we need to have some testing techniques, we need to have some quantitative things which we can define the reliability. And that's where this military handbook was developed, started to put together, and then the next 50 years, it was the basic, Bible on reliability engineering. So that was the one which people used always. Every reliability one referred to military handbook. Then this millennium, it has been maybe a little bit more scattered, but also, as I said, these modern tools for reliability analysis nowadays, they are of course softwares. Then they rely on the same principles. The models have been developed, the component libraries have been developed, and so on, but still the basics are there. That's why I wanted to highlight this. So this is another, let's say, case example, which is, I would say, quite obvious, and I already mentioned it, I think, on Tuesday, that the development is really rapid. First of all, we need to utilize kind of the same components, having adequate reliability on some applications. We are using them into more challenging applications, and challenging, what I mean with challenging is that they are either from stresses point of more challenging, or they are from the requirements point more challenging. And this simple example here of an airbag module is of course, in that sense, good example that it's both. First of all, the accelerometers, which are of course the critical components measuring the acceleration. Here they might see during their lifetime like quite much more that, for example, you could have the same components in your mobile. But if you think about the stresses in cars and stresses in your pocket, they are different. But maybe even more important is that the reliability requirement. If the accelerometer here fails, okay, it's annoying, but nobody dies. But if the accelerometer here fails, then somebody might die or get at least very badly injured. Either if it, let's say, misinterprets the deacceleration in that sense that the airbag is launched without good reason, then at least the driver broke his nose and face. Or then if when there's a real crash, the airbag does not inflate at all, which is of course even more problematic. So you need to have the actual measurement, but then of course you need to have the other electronics which makes the decision that, okay, now should I inflate or not the airbag. And of course this needs to be done in a fraction of a second. When the accelerometer starts to measure that, okay, now the acceleration is more than even emergency braking, you are hitting something, then before your face hits the steering wheel, everything must happen in that fraction of a second. So here is a little bit more modern. So this one was from Toyota Prius, I think already almost 10 years back. This is a little bit newer version from, if I remember correctly, it was Ford Focus, the same thing. But basically, here we have the kind of the same components. And for example, here is the, if I remember correctly, this is this Bosch component is the actual IC which is making the decision, inflate or not inflate. So just Google Ford Focus airbag or something like that, you will end up in this page, and you will see not that much, but at least some more details. What are the functionalities of each component here? So more complex devices and more harsher environmental stresses and tougher reliability requirements. So this is basically having exactly the same things in a verbal way. What I would like to highlight here is that the only thing is that when we are building a more complex system, then even the components themselves are as reliable as in simple system, then the more complex system has always worse reliability. Kind of sounds a little bit strange, but the problem is that when you have more and more components in series, because typically most of our products are, you can consider them as a series. Of course, in some very high reliability requirement products, we have also some redundancy, so we have parallel systems. But let's not think about those. So if you think that you have 10 components in your system, then basically the failure rate of that system is just sum up of all those components. If you add one more, even it has a very small failure rate, it still adds to the system failure rate. If you put 100 components more, then it definitely decreases the failure rate of the whole system. So it means that even the reliability of our individual building blocks is not decreasing, or even it might be slightly increasing. But when the systems are coming more and more and more complex, then inherently the system reliability goes down. So that is something that I would like to highlight here. The other thing is that because the development cycles are coming faster and faster and faster. So again, these handheld mobile devices, there maybe the trend is most obvious, that you need to get the new model out every 1 year or 1.5 years or something like that. If you don't get your new model out, then the markets think that you have some problems. Your stock market will be, let's say, stock value will be decreasing, and so on and so on. Maybe you remember Intel had this problem with their one of the newest processor components, maybe 2 years back or something like that, and they couldn't launch. They promised that, okay, we will have this new version or new processor component available, but then because of the technical problems, they couldn't do it. They couldn't verify the reliability or whatever. They couldn't do it. They couldn't launch the product. Then there was a huge drop in the stock value. So we need to get things faster and faster in the market. And that means that your reliability efforts are left in minimum. So you don't have the time to test. And on the other hand, you lack relevant field data. Because if the development is going faster and faster forward, then of course you cannot use the data which is coming from the field anymore, because it's already, you have changed so many things. So it means that you need to try to sell your reliability efforts to your management that, okay, this is something we need, otherwise we will lose money, because typically the managements, that's the only way to justify that I need some resources to do my work, is that because if you don't give me the resources, time, money, then you will lose more money because we will end up problems. So it can be avoidance of repair cost, it can be avoidance of warranty cost, it can be avoidance of loss of reputation or whatever. So few words on how reliability can be defined in different ways. So quite often in the reliability programs, you see that the reliability is defined like this. It's an interdisciplinary science aimed at predicting, analyzing, preventing, and mitigating failures. So first of all, interdisciplinary. What does it mean? It means that electrical engineering cannot handle reliability alone. You also need the assistance from mechanical engineer and chemical engineer at least. There might be also some need for mathematician to do the statistical analysis of big data and so on and so on. So maybe interdisciplinary, but mostly within engineering topics, I would say. Science, again, in quotes, because it's not science in that sense that we don't have Maxwell equations which would ultimately give the answer for all our problems. No, we have, as I mentioned already, problems are that you have several different solutions. Solutions which are better from one point and the other solutions are better from another point. And then what you want to do, you want to predict, you want to know when this problem could be happening. You want to be able to analyze why, where, when. You want, based on those, you want to prevent the failure. And then if it's not possible to prevent the failure, then at least mitigate the effects. So if something fails, then the consequences are not that high. This is few other definitions. So one thing which one kind of always needs to consider is that the customer defines what is reliable and what is not. It's if something is not working as the customer thinks, then it's unreliable product. Even you say that, oh no, it's working as we planned, as we decide. But if the customer thinks that he or she has purchased something which does a certain function with certain way, and it's not like that, then it's not a reliable product. It might be a question of communication, specifications, and all these things. So it's not just a hardware reliability. I think this is maybe the best definition for reliability. It's that when the customer comes back, but not the product. It's from Suvio's book. And then the last definition, which I kind of try to highlight here in this course, maybe our approach could be like this. So the reliability of a product is the ability to function under given conditions, specified period of time, and without exceeding acceptable failure levels. So three main things. First of all, we need to understand the conditions. I have mentioned it already too many times. External conditions, internal conditions, or environmental and functional conditions. Specified period of time. We need to have some kind of a target. We do not over-engineer. It's no sense to design again this so that this would work 20 years. Nobody would use, or practically nobody uses mobile phones which are 20 years old. At least 99.9% of the people don't. And acceptable failure rate. So what is, because always there will be failures during the operational lifetime because of overstress or something like that, how low we need to push the acceptable failure rate, because that's also a cost issue. So these things we will come back in the coming lectures. So quickly, I think we have 2 minutes time. So just a few more slides and then we can call it a day. So years of service. I think these are quite obvious things, so I will go these through quite quick. So if we think about different fields, then it's quite obvious that we have different expectations. Even disposable electronics. So nowadays there are, in medical field, there are disposable electronics. So basically something which you use only once. You measure something only once, or you attach some pads to your body and measure something only once, and then they are disposed. So the lifetime could be just 10 seconds, or it could be 2 days or 1 week or something like that. And then the other extreme is that when we are talking about military or aerospace or space electronics, so then we are talking about even up to 50 years of reliability. So, and then most of our products are somewhere in between. And it can be even within a field quite different requirements. So this is, again, I took an example from power electronics. So if you think about, let's say, some kind of a power component or model, what is the expected lifetime of that in different applications? Then concerning years, there's a difference, but also concerning operational hours, there's a huge difference. So just sorry not to go too much overtime, but one more slide and then I will finish. So acceptable failure rate, because we are coming back to this one. So already mentioned that we need to be aware that a failure somewhere is much more critical than in some other application. So therefore we need to define the acceptable failure. Which number, so is it that one product out of 100 products can fail during the first year of operation, or is it that one product out of 10 million can fail during the first 10 years? So that's a huge difference in how much effort we need to put on our reliability design or reliability engineering. Okay, sorry, 1 minute overtime already. Let's I will stop the recording